Hi, good afternoon, everybody. This is Barb Webb with D3 Technologies. Happy Friday to all. I want to thank all of you for attending today during lunch. I hope that you grabbed your lunch, and I want you to certainly sit back and enjoy the Aerospace Industry webinar. Before we get started, though, I would like to let you meet the experts here that you're going to hear from today. First of all, Lisa Castillo, she's 3D Systems Regional Sales for Production and Metal. We have David Cullen on the line. He's Aerospace Solution 3D Systems Application Engineer. And also we have Additive Manufacturing Technologies, Luis Folger. He is the Post-Processing Solutions, and certainly we have all three personnel that are going to be full of information today for you guys. I would like to make note that if you could jot the questions down in the chat box at the end of the webinar, we will be monitoring those and we will answer each question. So as I mentioned, I'm with D3 Technologies. We're a partner of 3D Systems. We've been with 3D Systems for about 10 years. The main reason that we partnered with 3D Systems is simply because we felt that 3D Systems had the widest breadth of print technologies. Certainly, they also invented 3D printing 30 plus years ago, and with some of their hardware, software, and materials, as well as their on-demand services, they certainly are on a mission to help transform businesses through some of the manufacturing innovation. D3 Technologies is an engineering and design consultant. We were founded in 1998. Certainly, we're one of Autodesk's largest resellers in the United States, but we focus primarily on manufacturing and help to increase some of that engineering efficiency through optimization, implementation, training, technical support, data management, and also automation. So we certainly look forward to talking with you today. I would like to go ahead and turn this over to Lisa Castillo, but here is our contact information should you need to reach out to either one of us at the end of this presentation, or if you don't get a question answered.
Hi, thank
Lisa?
you, Barb. Yes, can you hear me, Barb?
Yes.
Okay, wonderful. Again, welcome all of you. I know that some of you actually joined us from different time zones. We want to welcome you for attending, and I want to let you know that you are in for a treat. David Cullen is our Director of Application Engineering, and he brings an extensive background in AM production, in additive technologies, applications, as well as business planning. So without further ado, I'm going to hand this over to David.
Thank you, Barb. Thank you, Lisa. I'm going to go ahead and share my screen so we can kick this off. Hopefully everybody can see my screen. So once again, my name is David Cullen. I'm the Director of Application Engineering, and over the next 20-25 minutes, I will present some real-world solutions of additive manufacturing in the aerospace market. I would like to take the time to thank Team D3 for hosting this event and inviting 3D Systems and AMT to present today. I've been in this industry for 23 years, and I actually was recruited from the aerospace industry when I started my second career in this, and at the time it was called rapid prototyping. So our founder, Chuck Hall, started this industry in 1983 with the first patent application for SLA. Matter of fact, the file format STL was created primarily for rapid prototyping, and it actually stands for stereolithography, even though you'll find some places where they think it stands for standard tessellation language. But it is a product that was made so for the technology at the time, we could actually start to use this incredible process that Chuck Hall had dreamed up. 3D Systems has over 2,500 personnel and 30 offices globally, including 12 customer innovation centers. And at this point, over the last few years, we've seen a big move from prototyping and functional testing into actual real 3D production. The technology now has advanced to the stage that it makes it possible and delivers the benefit manufacturers need to see, such as durability, repeatability, productivity, and of course, improved total cost of operations. As Barb did point out, 3D Systems did start this industry with Chuck Hull's first invention. And currently today, we offer 6 separate technologies. We also have 8 complete different software suites, including some suites that are actually in the subtractive and traditional manufacturing realm. We'll talk about that a little bit later. And we have well over 120 materials and growing quarterly as we add new materials, softwares, and technologies to our portfolio. And before I get into the meat of this discussion, I did want to point out that if you visit 3dsystems.com, there's a lot of information that you could download. For example, I just listed a few. We have a lightweighting ebook available for download. We have a DMP inspection brief, and I actually have one slide on that later on that talks about this new capability. We have webinars such as onboarding with metal additive manufacturing. This is going to be based on validation in some industries that require quite a bit of validation certificates. We also have one coming up in a couple of weeks, all-in-one metal AM software demo. This would be our 3D expert. And then, of course, there's tons of case studies and success stories. You could go on there, you could actually find the industry you're in and all of the stories and webinars that focus on your needs and addresses some of what you would like to learn about. So this picture here, of course, is the SpaceX Raptor engine. And I wanted to start off by showing the picture of this because people may not realize this complex engine has 72 added manufactured parts on there. 50 of them come from 3D Systems. But it does show the fact that as we go forward, the capabilities of additive manufacturing are growing. This includes improved functionality due to the freedom of design, or in other words, removal of traditional manufacturing limitations. And I want to be clear on this. We look at additive manufacturing in 3D printing as a complementary to traditional methods of manufacturing. It's not going to replace it. It's not a end-to-end all solution. It's just another tool in the toolbox. In addition, as we go through some of these studies that I'm going to show today, you'll hear a lot and see a lot about component consolidation, topology optimizations, stiffness to weight ratios, and this is all made possible because of 3D printing. So in this webinar, we're going to concentrate on one of the vertical markets on aerospace because it is a exciting and growing market in additive manufacturing. And there is a large interest in applying AM to the aerospace industry. But like any other heavy regulated industry, it does face multiple drivers and challenges to success. And we're going to try to go over some of those. But that includes a drive to reduce weight, to reduce fuel requirements, a need to address your supply chain efficiencies, including MROs, maintenance, repair, and overhaul challenges, or PMA challenges for the aerospace industry. There's also a really big need for reliable certification of additive manufacturing technologies and materials for the aerospace applications. At 3D Systems, we're trying to deliver these technologies and materials and advanced expertise to enable commercial and defense aerospace OEMs to build 3D production into their operations. So we're going to be going through, and some of these, I'm not going to go through all of these, but if you look at rapid production of airworthy parts, one thing that you'll see in one of our case studies is antimony-free casting materials. Okay, this allows rapid shell investments to make very, very large parts for the aerospace or your supply chain to be able to reduce the cost of inventory through on-demand production of parts instead of having that physical part in your inventory. And of course, lightweighting, as we look and we all understand the needs to get to reduce the fuel requirements. So new designs free from the traditional manufacturing constraints allows you to have these new designs that are lighter and yet stiffer or do a better job or have better efficiencies for the aerospace. Now, we also work in production in the defense R&D world. So whether it's the Air Force Research Lab or the Army Research Lab, DARPA, you'll see a few of them in this webinar, Newport News, or the University of Dayton Research Institute. Matter of fact, one of the things that have just came out in 2019, in July of 2019, 3D Systems signed a contract with the ARL to build the largest and fastest direct metal printer. And the success and knowledge we gain from here can be easily translated to commercial applications in the near future. So this was signed last year, and a couple weeks ago, there was another story that came out. So if you look at our latest Factory 500, which is 125 liters, it's a 1/2 meter cubed metal printer, and it's one of the biggest on the market. Yet a couple weeks ago, the ARL updated, and we have a 1 meter by 1 meter by 0.6 meter metal printer that we're working along with the ARL to make larger parts that are validated for production. I mentioned earlier with our hardware and our software and material solutions, I also wanted to make an addition that one of our services, besides on demand, is we offer our customer the CIC. And it is a customer innovation center. It allows customers to come in and see real world applications. They get to see all the technologies working. They get to see the validation. Our one in Denver is really heavy in medical, so you get to come in and see how a heavy regulated industry works within additive manufacturing. And we have 12 of these around the world, and you could actually really go in. In addition to these, we also have several offers and services. Just not training, just not benchmarking or application support. We do have some part manufacturing, but the biggest part is when you look at some of the engineering, consulting, or validation partnerships that we could actually have. And we could help get the part not only tested and validated, but also optimize the design for additive manufacturing. And this is the reason why we do call them our customer innovation centers, is because we did make them for our customers and in-use parts. So now that I've gone through the required marketing fluff, I'd like to start on some of the solutions that are offered that our customers has faced in aerospace. So this first one here with the U.S. Air Force and DARPA, I had mentioned earlier about DMP inspection brief that we have. So what you're seeing here is how do you tell your part in metal? This is a metal machine. So how do you tell your part is fully has proper fusion? There's no porosity, and it's going to pass and work like you expect it to work. And this is a big issue because metal is the least mature of all of the additive manufacturing technologies that are out there. So we went into a partnership with the Air Force and DARPA, and I'm happy to say that we just released DMP inspection. So I'll explain this a little bit. On the left-hand side on the screen up there, you see a picture. That is called DMP vision. It is basically a perspective corrected picture of every layer. On the right is the same layer that's called DMP melt pool. And that is a photodiode melt pool analysis of every scan and every vector and every layer. And we record this, of course, and then maintain the data. Well, we just released DMP inspection that actually uses both of these technologies and is able to determine how well your part fused, if there's any porosity inside there. Matter of fact, our data has shown that we've been able to identify porosity 100% targets, anything greater than 200 microns or larger, and compared it to a CT scan. And if you go below that, we still, anything greater than 150 microns, we're still able to maintain 95% accuracy. And this is continually to be improved. And we still, even when you get down to small particles such as 50 microns, we're still able to identify the vast majority. But this will allow you to be able to have quicker validations and certificates for your metal printed parts. When it comes to certification of plastics, 3D Systems is constantly researching materials for new applications, such as a clear FR material for backlit panels or high performance FR polymers. So whether it's an FAR, a mil-spec, or UL94V rating, we're constantly looking to improve and apply these new materials to the market. Now, fuel economy, once again, one of the biggest drivers. I have read, different cost analysis for sending a part into space, whether it's geosync or further out, and the amount of money it requires to send a part into space. And this is true for the life of an airframe that may be 30, 40 years, designed for 30 or 40 years of service. Right? Could you imagine cutting the weight off of that over that span would save millions and millions of gallons of fuel. So this first example was a unmanned aircraft system. In this particular one, we used HST instead of a carbon field, and this allowed the customer to achieve a high performance based on a lightweight polymer. We used it with our SLS Pro X500 machine, and it did reduce the supply chain, improve the weight reduction, and of course, this could be applied in many applications on a UAS or UAV. Now, this particular one for the Airbus Defense in Space is a unique application because RF antennas and waveguides have been built the same since the 30s, 40s, and 50s with very little innovation in them. They are efficient, they're very complex to build. And in this particular case, we were asked if we could build with the freedom of design, if we could build a better RF antenna. We used an aluminum alloy and one of our metal printing machines. We were looking for weight reduction. We were able to take 30 parts and consolidate them into one part, and we produced it 50% faster. It is actually in flight on a satellite as we speak. But what is another outcome came was with the new designs and the freedom of design, we were actually able to improve the RF performance. Okay? If you look at this design up there, this is something unique, and it was just difficult to do it and impossible to do it with traditional manufacturing. This here combustion chamber is a really unique story. And keep in mind, when I said the case studies were on 3D Systems, every one of that you see here, you could go to 3D Systems and get a full detail, but for the sake of time, I'm trying to give just a high-level overview of this. But this combustion chamber for the European Space Agency was made out of titanium 6-4, And it did have even a component reduction of 5-to-1. But if you look at the original bulky design, it had an external scaffolding. And we improved this by just applying an external surface lattice structure. And it was able to achieve everything that the ESA was looking for. And of course, with the software, this made it very easy. But there was two problems that we were trying to solve. One, the original design was bulky with a scaffolding because it had to be able to handle a non-operational transient load. In other words, leaving our planet and leaving our orbit, okay? So during this time, it had to be strong enough to withstand all of those stresses of launching. But then when it got into space, it had a completely different set of operational requirements. And we were able to achieve all of this with direct metal printing and our expert software. Now, you may have seen this one. This one's been out for a little while. This was also, the first set was put into flight in 2017. But one of the things that you may have heard in the industry is the buy-to-fly ratio. So, for an example, there is on an F-35 a bracket near the rear of the engine that's made with TI-64. And they have to take a 15 kg block of material and they whittle it down to 500 grams for this bracket. Okay. So where are the other 14.5 kgs? Well, they're on the shop floor or inside the machine. Whereas you're able to build the part that you need with topology optimization or a optimized additive manufacturing design without that waste stream that you have with the buy-to-fly ratio that is so prevalent in today's market. We were able to print this not only in titanium, but we reduced the weight of the bracket by 25%, reduced the production time in half, and yet we were able to improve the stiffness to weight ratio where it was required. Now, I will say, if you look at this bracket, there are 5 touch points that's on the other side of this picture here that did require traditional machining. So I do not want to say that this was printed as is, but our software was able to add a little bit of stock, produce the codes, and it was easily machined off on the 5 touch points where it actually attaches to the satellite. This particular example right here is our SLS technology. This happens to be a nylon 12 product. And what we were able to do on this particular example was it did have combined complete assemblies into a single build part, which actually was lighter, less labor, less resources required for assembly, and there was no tooling. So it was a true on-demand production part. And this particular was for the Apache helicopters. But you see this in a lot of places. The F-18 ECS pods went from 400 down to 27 component consolidations. And we were able to reduce the inventory requirements. Bell Helicopter bulkhead environmental ducting is now produced in one piece in SLS with our nylon 11 EX black material. So you see a lot of these examples of being able to not only make it lighter, but also reduce the inventory requirements, assembly times, and thus the errors of assembly. In this particular case, Metro Aerospace has been providing these micro vanes. They're also built in SLS with a glass filled. And as you could imagine, they go through extreme testing because on the ground, it's not uncommon on a tarmac to have over 40 degrees C temperatures. And of course, when they're flying at altitude, it's not uncommon to see minus 40, minus 50 degrees C, and the temperature cycling. So they were looking for material and a product that can withstand those extreme environments. And what this was able to do, because as you know, in every one of these placements, the fuselage design is slightly different. So each of these are slightly different as they go based on the location on the fuselage. So they're not just mass produced. They are produced with a slight variation. And we were able to help reduce the fuel consumption by 3%. And once again, this is with zero tooling, and you could do it on demand. Now, I mentioned earlier that as much as I love 3D printing, it is a complementary to traditional. And this is a perfect example where a traditional manufacturing was used. And 3D Systems used our Gibbs CAM, CAD CAM software to help produce this complex CNC machining for the Mars exploration rover. And that's the wheels that they're going to be using. Now we're going to get into a little bit of rapid production of airworthy parts. A couple examples here. So in this particular one, we provided a solution using our Acura Cast Pro Free. It's an antimony-free material. And this allowed several things for the customer. Very rapid production of casting patterns. It allowed them the ability to add more complex designs into their casting process. And they were able, even with this improvement, to significantly reduce the cost of casting patterns as a whole. Okay, this just basically means that casted parts could be produced far faster with more flexibility at cheaper cost than some of the traditional alternatives. And keep in mind, 3D Systems is always looking to improve this. So keep tuned to 3D Systems and or your partner D3, because we'll be looking at improving our quick cast capabilities, including printing faster, reducing material consumption, and of course, reducing the ash content, which is so critical in these applications. So in this particular one, this is another software solution that we have. Our GeoMagic Control X is a metrology based, so you're able to scan and see the accuracy of a part that was designed. And this goes along with our GeoMagic Design X and ability to scan in a part and reverse engineer it. And this is really important for parts that may no longer have the OEM or the PMA that's actually in business producing these parts for older aircraft. Now, wind tunnel testing is really big, is really a large industry in Formula One, but it's also a big part of the aerospace industry when it comes to testing and designs and getting the most out of any given design. So this allows for increased complexity of models. You can see in this picture, we have integrated pressure tappings part of this actual model, okay? And with 3D printing, the preparation of those taps go from 1 per day manually to about 1 per minute in this particular model. Supply chain. Of course, this is a big cost for airlines and actually for almost every industry. And how do we actually help transform the supply chain with end-to-end solutions? In this particular example, we used our GeoMagic Design X to scan in an actual part. We were able to reverse engineer it and made a few minor improvements on the design, and then we printed it in SLS with an FR nylon 12 SLS material that actually complied with the FAR 25 fire requirements. And we were able to also reduce the weight by 15% compared to the original part. Of course, this also allows for you to have the on-demand instead of having an aircraft down. I think everybody has heard of aircraft, people pulling off their luggage and hitting an exit sign. Okay, and a broken exit sign is a red X item for an aircraft. Why should it be grounded when you could print one instead of having it flown over from wherever your physical inventory is, if they have it in inventory, and lose that revenue? This is another solution. So it's not always 3D printing, but this is another perfect example of software coming to the rescue. In this particular one, during, it just saved the cost and money for the Royal Air Force. And in this particular example, we used the 3D scanning, Geomagic, reverse engineering, and inspection software. So we used both of them for the Royal Air Force, increasing accuracy of their custom fitted parts that were being produced. So we were able to reduce a fighter ground time from 6 weeks down to 3 days. So some of the legacy equipment, or whether it's an old aircraft that's no longer being manufactured but is still flying, or in this particular case, a legacy design for the Apollo F1 engine, just no longer existed, and the 2D blueprints were also very incomplete. And this caused a huge issue for NASA when determining how to rebuild some of these rockets and improve them for modern space travel. Of course, with our scanning and Geomagic software, we were able to build accurate as-built 3D data of the entire assembly within 4 months. It's quite an accomplishment, considering that NASA felt that they would not be able to do this at all. And here's a perfect case of an MRO team for Northrop Grumman, and they were having issues with hard-to-reach areas of the planes that were requiring some aircraft disassembly. And working on aircraft myself, I know how tight some of those places can get when you need to do repairs and or supplemental type certificates or upgrades. And of course, with the assistance of the 3D printed repair kit, the teams were able to provide a very clear work path to access hard-to-reach parts for repair without having to disassemble large areas of the aircraft itself. This enabled a very fast and cost-effective repair in the field. This particular case right here was a German aerospace liquid rocket engine injector. Of course, you see the part reduction count, so component consolidation is a big capability, okay? And if you look up in the CAD drawing up in the upper right section of this slide here, you'll see that the injection head flow volumes, the blue is your liquid oxygen, your orange is your kerosene, the red was the film layer, and your green is the transpirational cooling, okay? This would have been impossible without additive manufacturing. And it was built with our DMP 350 using nickel 718 as the alloy of choice. Here's another scanning solution that we helped with EasyJet. What they were trying to do is, as aircraft run into different storms or have different damage, whether it's on the ground or during the flight, you have to have a powerful way to inspect any damage or any change, okay? This allows for the management to make a proper decision based on the repairs and based on this data, okay? And of course, we use our Geomagic Control X software. Be able to show what kind of, in this particular one shows some of the damage on the flight surfaces. So as I start to get near the end of my presentation, why would you look at 3D systems? Well, it's really nice that we started this industry, but we're definitely not the only players, and people like Scott Crump and University of Texas have added to it, and everybody else out there. has really enabled a brand new market and capabilities. But we are integrated with all of our portfolio solutions, whether it's technology, software, hardware, materials, and we have been able to provide some of the biggest solutions for our customers. Okay, and we're also a founding member of the America Makes team. So as I close out this part of the presentation, I did want to show you, I did steal this slide from one of our webinars that are coming up in the next couple of weeks. And this is an actual real aerospace bracket. It's a real solution. I only wanted to show a couple of slides from it, but this is how you could actually make additive manufacturing as part of your process flow. So from the very beginning of Design X, we took a design that actually had, was designed with traditional manufacturing in mind. Okay, so they had all those limitations, and you could see on their design, it was heavier, it was bulkier, and you could clearly tell it was made in the subtractive kind of environment. And we were able to go in there and use our Design X and Expert to make some changes for additive and actually improve the functionality, reduce the weight. Okay. The next slide where it says prepared is using our 3D Expert, and the slide above that does show our simulation of where our stresses are going to be. So we were able to run through this design with a algorithm that actually allowed the FEA to produce where the stresses were going to be. And sometimes these could be minimized with maybe a design change or just orientation and or how you support the part. Then of course we printed it in DMP Flex 350. The next one under inspection, you see two sections of inspection. The top one was DMP monitoring inspection. I spoke about that earlier. So we were able to use our monitoring, which is the vision and the melt pool, and the inspection to make sure that there was no lack of fusion or porosity issues in this part. In addition, after the part was done, we were able to use our GeoMagic Control X and scan the part in and put it over a color map over the original CAD data to see what kind of variations that may be present there. Then, of course, since Expert is built on Semitron, which is a CNC prep software, it allows us to look at any post-processing through traditional manufacturing methods, CNC, milling machines, whatever it may be. And we could look at that because it is built on Semitron, which is a subtractive software. The next two, the machining and the Cut AM, is not a product of 3D Systems. It is a product of one of our partners, George Fisher, but it could be any CNC machine. But the Cut AM, I do want to say that was uniquely made for our new DMP 500. So it allows the very large plates, which are 510 by 510 millimeters, to be horizontally EDM'd off. It's got a rack to catch the parts so that you don't have the problems of a part possibly falling into the area and jamming up your EDM. So it is a design that was made by George Fisher with all of their subtractive and EDM experience based on being a partner with 3D Systems. And then of course you ended up with the final part. I did want to show you a little bit closer up on some of the layout on the machine that will be on the left using our Expert software and how we optimized it. And then a little bit of a close-up shot showing what kind of supports. You can see there's two different types of supports we were able to use, also with a stock allowance on the bottom for the EDM to cut off cleanly. And then we showed a couple of the darker gray areas where we optimized the design for additive and then added a little stock on there because the end customer wanted to have a super finish on these. Matter of fact, somewhere close to a bearing surface finish. So we added a little stock and produced the CNC code to have it post-processed to within the customer specifications. So that ends my part of the presentation. Once again, thank you for joining us. I know there's a little bit more coming on with Luis Folgar and AM Technologies talking about their post-processing. So at this point, I will turn it over to them, and thank you very much for your time.
Thank you, David. Thank you very much to Barbara with D3 and also with for 3D Systems for allowing us, giving us the opportunity to join your webinar. David, if you don't mind, we'll go into our presentation. And my name is Luis Folgar. I am the Chief Technology Officer with Additive Manufacturing Technologies. And we are a company that is headquartered in Sheffield, in the United Kingdom. Our headquarters here in North America are in Austin, Texas. And we have a very diverse portfolio of technology solutions for post-processing. From the time that your parts are done out of the printer until they're ready to go in use, we have been able to deliver innovation around technologies that are sustainable, that reduce the efficiency, that reduce the labor and create efficiencies for the cost of post-processing, and also that improve the performance and add value to the parts. So with that, I'd like to give you an introduction to the portfolio of technologies that we got. So if we can go to the next slide. I want everybody to know that we have a full engineering and design capabilities within our company. We manufacture in Veszprém and our Veszprém in Hungary, but our capabilities for engineering and design are also in Sheffield, where it's our center of excellence for innovation and R&D, as well as here in Austin, Texas. We do a full service support and research and development for the aerospace and defense community in the United States. So it's a pleasure to be part of this very focused webinar around aerospace, because our technology, I think, David, you did an excellent job at emphasizing how additive manufacturing really is complementary to traditional manufacturing. In the same way, we feel that our technologies, our post-processing technologies, are certainly complementary in a lot of respects, like in the case of Post-Pro 3D, essential for end-use parts and certainly for aerospace parts. So with that, we can move on to the portfolio of technologies that we develop. At the center, we got Post-Pro 3D, which is our flagship product. It's where the company got started around the surface engineering and surface finishing technology, which we have an exclusive license from University of Sheffield to develop equipment and further commercialize the technologies for the solutions that I'm about to dive into. But we have been able to use this flagship product and the core technology of a very sustainable controlled surface engineering method and develop the technology for an industrial package. And with that, we've been able to scale it to a miniature size, what we call the Post-Pro 3D Mini, and also scale it for production, what we call the Post-Pro 3D Pro. So it is essentially the same surface finishing technology, the same surface engineering methods. It's just different configurations that cater to different industry verticals and different types of end customers. And if you're very familiar with post-processing and with surface engineering, surface technologies, you will appreciate that the biggest variable that you will have on your parts comes not necessarily from the finishing process itself. Well, sometimes it does if it's a manual post-processing, for example, but a lot of times comes from the upstream processes like cleaning, support removal, depowdering, and for us, that variability is unacceptable. So the next logical steps was to develop automated solutions that can remove that variability from the upstream post-processing methods. And we have post-pro DP, our depowdering automated technologies that we are introducing to the market. All of these technologies are focused for polymers. You know, we have had a strategic focus on polymers, but we have a roadmap to metals as well. So I know many of you come from the metals world and are very much interested in metals. So I'd say stay tuned, because the company is rapidly developing technologies in those areas as well. So to dive into the next slide, David, the technology, just to like emphasize the importance of it, anybody that has produced parts and truly analyze the surface of them and some of the failures and try to do a root cause analysis on why they fail, they might have encountered the root cause comes from the surface. A lot of the imperfections that come from the surface are because of the material we're working with, powder-based technologies. In this particular instance, it could be extrusion type of technologies, like, you know, the filament type of technologies. But in this particular case, you know, we are talking about aerospace parts. We're talking about using, you know, high-end technology provided by 3D Systems, high-end materials that are already good. Those technologies have been dialed in, improved, and, you know, and a lot of times overly engineered to be able to deliver flight parts quality and meet very strict performance requirements. And we get the value added of very tight tolerances. We can meet the tolerances, we can meet the throughput of the part, we can sometimes meet the performance, but when it comes to the long-term life performance of the part, a lot of times you'll find out that a 3D printed part will fail, essentially because the surface treatment has not been properly addressed. We're talking about applications where you have, you know, high cycle fatigue, where the part is under a lot of bending stresses or under tension, like in, you know, high vibration environments, for example. And most of those failures really come from the crack initiation sites that are on the surface. So our technology, the post-pro 3D technology, is able to address that challenge in a very, very innovative way, using chemistry and physics in the engineering that comes with the equipment. So I'm going to jump into the next slide that will also emphasize, we're talking about being able to address the 50 to 100 micron area within the edge of your parts, where the partially fused particles are. You know, you have good parts produced by great, very capable printers, but these parts can be better by addressing a chemical process that, you know, a controllable chemical process that addresses the surface imperfections on the part that may come from the materials themselves, sometimes, as you saw in some of those micrographs early on. It's, David, next, if we can go to the next slide. One of the unique features of this technology is that it's controllable, so there is no line of sight issues. We're talking about, you know, we're not removing material, we're not adding material. We are talking about using what is already on the surface and reflowing it and using it to our advantage to fill in all the surface porosity and get a very smooth, a very uniform surface for these parts. And in turn, by having these capabilities and these controls, what you end up is a surface that it's sealed, has a much better water absorption performance. It's a surface that can withstand pressures. If you are 3D printing vessels, for example, that need to be pressurized, they will be able to sustain gases. And it also, as I said earlier, it erases the crack initiation sites. So with that, you get much better elongation at break. Elongation at break is a critical mechanical performance for the material and for the parts that, that you're producing specifically for aerospace. And with that, you also see an uptick on the UV resistance because there is a lot less moisture absorption at the surface, and there is a lot less exchange with the exchange of the evaporation of that moisture and the sunlight affecting the mechanical properties of the material. So all the issues really start at the surface. So because of that, we have tackled the surface to provide this type of capability. So we thank David Cullen for the invite, and we also thank him for constantly run applications through us. We have an ongoing collaboration with 3D Systems. It's been a very good collaboration. I think what we have found out is that it takes this type of collaboration for us to understand truly what we've developed. It's a technology that many of you may think that is only addressing aesthetics of the part, but through the partnership with 3D Systems, we've been able to quantify and measure the capability of the technology and the value that we're adding to the performance of parts that are already good, and we're making them great. So to give you an idea of what the machine looks like, this is the Post-Pro 3D machine. The chamber envelope is 600 by 400 by 400 millimeters, 24 by 16 by 16 inches. I think it's a closed loop system, and I think what is important for you to understand is that we're not using water, we're using better chemistries, we're using less energy and less labor. We can go to the next slide. And the process, the way it works is you have a chamber that is under pressure and temperature. We rack the parts, and they are suspended into these racking systems that can be customized and standardized for production. Once we pull the vacuum and under temperature, we control the amount of chemical that is dosed. We use a chemistry that is green and sustainable. It is registered and approved by the, follows all the EPA regulations. And we are also going through FDA approvals for a lot of applications, but it has passed all the cytotoxicity, all the skin irritation testing, and basically we're working with a medical grade alcohol that is non-flammable inside a closed loop system that has been developed in a very safe way to be put into an industrial production scenario. So the parts go into the chamber, and the liquid chemical is vaporized. The vapors are introduced into the chamber, and as soon as those vapors touch the parts, they start working and dissolving the surface of the polymers. All that partially fused particles that you saw on those micrographs, we dissolve them and reflow them, and without changing the dimensions of the part. So there is no shrinkage, there is no gain in weight, and in turn, what you see is that for aerospace applications, the weight gain is very critical. So this will reduce the labor in finishing the part. It will seal them, and it will get them with much better performing properties. If we go to the next slide, David, we decided to take nylon 11, as David pointed out. 3D Systems is just an example. We have more data on multiple materials. The technology works with any thermoplastic that is out there in the market, 120 plus different thermoplastics we've been able to process, but we decided to take nylon 11 because it's the best performing material. EX Black is a phenomenal material that is the material of choice as far as polymers for the aerospace industry. And these charts give you an idea on the before and after tensile stress, the tensile properties and the uptick. Our technology will not change the tensile strength or the yield strength too much, but if we go to the next slide, David, you will see that we're also not changing the modulus, which is important because if we go to the next slide, we do have a significant gain in the elongation of break. Nylon 11, when you're producing parts with printers like 3D Systems, you can get the maximum elongation of break properties that are around between 50 and 60% elongation of break if you really are using the parameters that David has developed for performance. And after our post-process, that elongation at break will jump to sometimes, 200 to 225, 240% elongation at break. So yes, the parts, we do that without necessarily modifying the modulus. You may say, well, you're softening the parts, so you're stretching them more. That's not the case. We are retaining the modulus, which is critical. You cannot do that just with any single chemistry or any single process. So if we go to the next slide, David, I want you to note that you can go directly to 3D Systems with any questions about data around our process or any benchmarking that needs to be done. You can also contact us directly. We do everything free of charge. Well, not everything, every benchmark we do free of charge. And yeah, we're willing to talk to you about your applications, but I'd like to open the floor for questions, whether it is for David and his phenomenal presentation or any of our technologies.
Before we do that, Luis, thank you very much for that presentation. I do want the audience to know that it's absolutely true. Failure points start with an inclusion or a defect on the surface, and it could really reduce what you get from testing with a standard ASTM approved bar or DIN or whatever it may be. And I want to give a good little story that we hope to see a white paper out later on this year. But using 3D Systems SLS 6100, a third-party material that we currently do not have in our portfolio, and AMT's partnership, we did a real quick testing of a FR polymer. And I just wanted to let you know that here's 3 different companies with 3 different products, and we wanted to see how we could improve it. And although the part came out of our machine smoother and higher mechanicals with better recyclability than the legacy equipment, the fact was they would still wanted better performance. So we were able to send it off to Luis and his teams, and when they got it back, they tested the as printed versus the vapor honed system from AMT, the same part, built in the same blend, same machine at the same time. And they were able to reduce the surface roughness down 200% while improving the mechanical properties or elongation at break, I could say, by 260%. That's just one small little sample of some of the things that we have seen when you need a smooth vapor honed part as a final product. And it really has opened up people or style, instead of looking at ducting and environmental controls, or being able to look at additive manufacturing for more of the in-cabin solutions. I just wanted to point that out. Thanks again, Luis. And I'll turn this back over to Barb.
Thanks, David. And thanks, Luis, very much. So we do have some questions, and I'm obviously going to have David and Luis answer some of these. So I'm going to start out here. First of all, David, I think this is for you. What type of inspections are you using to help qualify parts? And do you see a reduction in defects with metal AM versus traditional manufacturing?
Good question. Well, there's a host of, statistical data capture that we use to show the health of the part. So it's kind of multifaceted in the fact that, one, we need to certify the materials and the OEM equipment. So our material certificates that we're starting to do with all the testing is the first stage. Then when you print them in the machine, whether it's plastic or metal, we use the data capture on the health of the machine. And for example, I showed the DMP monitoring where we have vision and we have melt pool. For an example of that is our vision will eventually be able to capture if you have what is known as a short feed, or if the parts were not fully covered on the next deposition of layers. And if we're able to catch that, because these are lights off operations. So guess what? If it happens at 2:30 in the morning and no one's around to see it, how do you know that it happened? Well, you have to have this data capture to be able to say, yeah, we had a problem there, and at least be able to give you a ability to make the right choice. And then, of course, with metal being the least mature of all and the fact that they're being put in vertical markets that require extreme certifications, with that, that's why we came up with DMP inspection to allow to look at lack of fusion, porosity issues. And even if you have 100 parts on a plate and one part separates from you have to now be able to have the ability to stop that one part and save the other 99 parts. So it's a combination of from the material certification all the way down to data capture to make sure that we could count on the part having the mechanical properties and the attributes and characteristics that we expect of the final part. That doesn't conclude or allow, or I should say, you still may have to do a sampling destructive testing, but guess what? You see that even in subtractive today. They'll take 5%, 1%, 10% of the parts and do additional testing to make sure, including destructive, that the parts meet or exceed what they expected. So it's a combination.
Okay, great. Here's another question, David. Does your validation of the part say that part contains no voids and meets the strength requirements of whatever material? And is this validation FAA, something that FAA would accept?
Yes, we're going down that path right now. We've got a lot more experience, I'll be upfront and honest, in validation of medically implanted devices and medical devices, whether it's instruments or implants. So both of them are highly regulated industries, whether it's medical or aerospace. And I think everybody's heard about the LEAP engine. And a lot of those validations are going forward. We're working closely with the FAA, CAA, and military and DoD products to ensure that we're going to meet them. But it's a long road, and every component requires a thorough look to make sure that we could print parts that are going to meet and have the life cycle that part does, whether it's a, show example is we're starting to do things like showing low cycle fatigue testing, right? We've never done that before. And that's because the industries are pushing us towards that type of testing. So it is beginning to become more and more of an application, and more OEMs are looking to roll 3D production into their process, but every part is kind of unique, and we need to look at it from a holistic view, depending on what the final product's job is.
Okay, Luis, this is for you, I believe. What do the finished machines cost?
So it depends on the type of system that you're looking at, and our standard piece of equipment is a system that can be delivered in different types of configurations. But I'd say between depending, it could be a range between $100,000 and $120,000.
Okay, and also can metal printed parts be post-processed for anodized, powder coated, etched?
Yes. So our process basically removes all the chemicals. We extract everything out of the parts so that there's no traceability of the chemicals on the parts. Even if you do, FTIR, mass spectra on the parts, you will not find a tracing of the chemicals. So that's how effective the process is done. So what that means is that there will be no outgassing, there will be no impact that is detrimental to a post-process operation like coating or painting or EMI shielding, anodizing, or electroplating.
Okay, and this is going to be for you as well, Louise. What kind of machines are you aiming to develop for metals? Are you working with the CIC in Denver? And I'm also interested in processes like herditation, patented by Hertenberger. I hope I pronounced that correctly, for our application development services at CIC in Belgium.
Yeah, you know, the development on, or the roadmap of development for metals is something that we got ongoing. A lot of that information is confidential, and you know, we can disclose more on a one-on-one basis if you are interested in learning more about that.
Okay. And David, someone wants to get your contact information. They'd like to contact you as well. So maybe we can provide that information to them via your email. Let's see. I'm getting a couple of people requesting David's contact information.
We'll do that on an individual basis
Yeah.
with their email directly.
How do you communicate with FAA, EASA for part certification? Is there a back and forth process between FAA designs and manufacturer producing prototypes until the FAA deems the design certifies and issues a type of certificate?
Yes, there is always communication going back and forth between the two agencies and us. And I think at this point, one of the best things that the audience could do is I highly recommend them to look at our webinar coming up on May 5th that talks about validating parts in a highly regulated industry. And a lot of those questions will be reviewed and answered during that. It is much more in-depth going through the validation process.
Okay. And I think that's all for the questions today. I just want to thank everybody. I want to thank David Cullen. I want to thank Luis Fogar, and I want to thank Lisa Castillo, all three of you, for helping put this presentation together. And I hope that everyone found this very valuable. And please don't hesitate to reach out to Lisa and I should you have any questions. So thank everyone. Have a great rest of the day and a great weekend.